Okay. So for today and for tomorrow, the plan is to start with chapter 1. And in particular, today we will just do a small introduction. So here we'll just try to explain what are we going to do in the semester. Okay. I don't think we're not going to do some hard math for this first like 15 minutes very quickly. And you know that the course is called Introduction to Fibrations. So the first question that we should ask is, what is a vibration? Yeah, this is like first question. And I believe you have both seen a vibration, which is a very standard one, which is the tangent space. And the idea is that you have a manifold, and to each point of the manifold, point on the manifold, we associate a space. Not necessarily a space, actually. We associate a mathematical object. So the examples you've seen is for sure vector spaces. So this is the case of the tangent space, yeah. But this could be something different. It could be a group. It could be a ring. It could be other topological spaces, other manifolds even. Etc. etc. Yeah, it could be really anything. And the idea is that we want this varying, so to each point was the space, we want this association to vary continuously. In a, well, depends on what category you're in. So you can think about continuously, or maybe you care smoothly, or you can even care about holomorphically. And we will talk, of course, of continuous vibration, smooth vibration, and holomorphic vibrations in these cases. The way to encode this, so how do we encode this? Do we encode this? So maybe the first thought could be, you say, okay, you take P and you associate something, yeah, some space, FP. So point space. This is usually very not convenient because it's very hard then to talk about continuity. You would need like to put some kind of topology on the space of all possible spaces. So this is not usually how we do it. So no. What we do most of the times is you consider something the union of all these possible FPs, and then a projection onto M. So kind of the inverse. And now if you want to look at this map, it's more like P goes to pi inverse of P. Yeah. And the point is we will put a manifold structure on this object. Yeah. And then we will ask, when we want to talk about continuous vibrations, we will ask that this map pi is continuous. And if we want to talk about smooth vibration, we ask that pi is smooth, and holomorphic vibration, we ask that this pi is holomorphic. Okay. So this association to a point to associate a space or a mathematical object is actually reversed. So you have a collection of mathematical objects, and each one of them goes to a point. Okay, and this corresponds to this. So let's see some basic examples. And the real basic one is is to every point, you associate just R. So in this case, it would be something like this. You take P and T, and you just send it to P. Yeah, this is our first basic example. This is so-called trivial fibration, which is a trivial bundle, but this we'll discuss later. There is a difference between fibrations and bundles. And even though the course is called Introduction to Fibrations, actually our objects will always be bundles, never just fibrations. So a bundle is a specific type of fibration, but we will discuss this later today, maybe tomorrow. So it's a very simple one. To every point, you just associate R. So you see that this, if this is our pi, your the anti-image of a point is, well, it is exactly P times R. Yeah. But we think this as the vector space R, right? So it's something isomorphic to R. So this was example one. Another example that you know very well is, of course, the tangent space. You know it, right? Both of you. Yeah. So in that case, we have the tangent space of M, and this, as I was saying before, we can think about it this way: is the union, disjoint union of all the tangent spaces in a point. And to each one of this, of course, we're going to associate the corresponding one. So tangent space, have you seen it in this way or only pointwise?
Yeah, I know it both ways.
Okay.
Usually I use it pointwise, but
Yeah, okay. So the standard is, I mean, you can define it pointwise. We will do anyway. We will review, of course, the first week, maybe week and a half will be just to review a few things. But yeah, here to every point, you can associate the corresponding tangent space. So point, tangent space, and then you just consider the union of all of them, like we were doing here. And the interesting thing is that this object here will have the structure of a manifold. So you can talk about continuity on this map, if this map is smooth, etc., etc. So these are, okay, so in the example here, of course, is that, and we know that TPM is just a real vector. I mean, if M is real, this is a real vector space of dimension equal to the dimension of M, right? So these are both examples where the fiber, the so-called fiber, so the object that we are looking at, are vector spaces. Here is just R, here's some R to the N, okay? And but let's look at another example. So something where the fiber is not a vector space. So let's say we have our vector space. Here's the eraser. There it is. We have our vector space TPM. We can consider its projectivization. See there, the projectivization of TPM. So if you don't know what this is simply the quotient space TPM minus 0. And 0 is considered the 0 as the vector space 0 modulo the equivalence relationship. Let's say that V is equivalent to W if and only if there exists a real lambda such that lambda V equal W. Okay, so just how you define the normal, the projective space. And of course, this lambda is real if we're talking about real vector spaces, is complex if we're talking about complex vector spaces. But for now, this is not important. And now, of course, you can consider the union of all of this. Yeah. And this, guess what, is what we call the projectivization of the tangent fibration. And of course, this map is what you imagine it to be, right? This is a disjoint union. You just send to the correct point. So this is a fibration. And P inverse of pi is isomorphic to the some real projective space, yeah. Correct. So this is our first example of, this is PR, so the projectivization of R to the dimension of m minus 1. So this is our first example of a fibration where the fiber is not simply a vector space, but it's something a bit more interesting. In this case, a topological space, the projective space. The last example I want to consider is the so-called frame bundle. So if we take P in M and consider all ordered pairs U, V in TPM times TPM, which are linearly independent. Linearly independent. Okay? And denote it by F stands for frame TPM. Yeah, so this is the set of all these ordered pairs. And so linearly independent ordered pairs, well, if you think about them, sorry, not pairs, sorry, my bad, because I was thinking dimension 2. So linearly dependent and tuples. So sorry about that. U1, UN in TP to the N, which are linearly independent and tuples. And N is the dimension of M. Okay, sorry about that. So what I really saying here is that this U1, UN should be a basis for TPM, okay? And so, okay, we have N vectors, they're linearly independent. And if you think about them as columns of a matrix, then this column will need to be of determinant different than 0, right? This is the definition of being linearly independent. I mean, not the definition, but it's equivalent, of course. So, well, this is simply GLN, or at least isomorphic to it in some way. Okay, do you see this isomorphism? I mean, maybe not. I'm not asking you that you be able to prove it, but these are N linearly independent vectors. And so if you put them in a matrix, this matrix will have determinant different than 0. So this is GLN. Okay. And of course, then we can consider the frame bundle, which is, of course, what you expect it to be. Into M. And again, to a point here needs to, a vector here, I'm actually a matrix here, needs to be in one of this. And so you send to the P, to the corresponding P. So this again is a fibration. And the fibers, so the anti-images of points, are somewhat isomorphic to GLNR. Okay. And of course, every time we say isomorphic, we always should be careful, because isomorphic as what? GLN is both a group, right? It's a group, but it's also just a manifold. So is this isomorphism as groups or as manifolds? And or even as something else. For instance, GLN, you can consider it as a group, but as a group, it's acting on itself, right? So is this also isomorphism maybe of a group action, right? So isomorphism of manifold together with group actions. And we will need to discuss every time we talk about isomorphism, what do we mean? For now, this is not important. Just think that the structure somehow resembles the one of GLN, okay? Okay, and once we have all of these vibrations, we're interested in studying them. And an important tool is the study of section. So, oh my God, sections of a vibration. So what is a section? Well, let's say we have this pi, which goes from some pi e to our m. fibration. And we don't really know what this means, right? We have no idea what this means. But we realize that this is how we encode this idea that to every point we associate the anti-image of this pi. And this should be some kind of mathematical object. So what is a section? So a section is a map S from M into E, such that if you do S and then pi, you just have the identity. So what this means is that S of P is in the anti-image of P. Yeah. So the way I imagine this is that here we have our M, and over every point you have some fiber. So this the union of all of this is like our E. Maybe I'll use colors here. Yeah, I can think of this like each of these vertical lines are fibers. So this is like pi inverse of P, and this goes to a point P, specific point P. Okay. And this section is what is a section is basically telling you it's a function from M to E. And basically over every point, you choose a specific point of the fiber. You choose one. This is your S of P. So this would be S of P. Okay. And then you move. So as this is moving, this is also moving. Yeah. So if this reminds you of graphs, because this looks a lot like a graph, right? You're perfectly correct, because our first example of a section is just for our trivial bundle. So we have pi, sorry, now I'm using bundle and fibration kind of as the same thing, but we will see that. So this is the trivial one. So we know we associate to P, T, we just associate P. And now what is a section? So let's try to just make up a section, yeah? So S of P, well, it needs to be in the fiber. So the first component needs to be P. And the second one can be just any real number, right? So, well, F of P, and F is just continuous, decay, whatever degree of regularity you want. Yeah. So sections of the trivial fibrations are nothing but functions, or well, graph of functions, let's say. Yeah. But you know, graph of functions and functions is the same thing. So fibrations are somewhat a generalization. I mean, sections of fibrations are a generalization of a function. Okay, well, with the trivial bundle, we recover this notion of function, but otherwise we have something more complicated. And actually, I believe you've seen some of this. If you look at the tangent space, yeah, so tangent bundle, tangent fibration. Then a section is what is called the vector field. Have you heard the term vector field before? Yeah. So over every point, you choose a tangent vector. This is a vector field. Okay. And it's nothing but a section. Yeah. Let's look also at PTM for a second. Now here is more complicated, a bit more complicated, because now over every point you have to choose. So to make a section, over every point, you have to choose not now you don't have to choose just one vector anymore, but you have to choose a direction. A non-zero direction. I mean, these two words should be swapped, but it's okay. To choose a non-zero direction, yeah? So at least in the real case, so this is equivalent. equivalent to finding nowhere zero vector field. Okay, so let's examine what I wrote here. So let's say you want a section here. So over every point, you want not just a vector field, not just a vector anymore, not just an element of TPM. You're satisfied with a direction in TPM. Yeah. And but the problem is that it needs to be non-zero, because if we look back at the definition of our projectivization, we're removing zero. Okay. So if we manage to find a vector field which is never zero, then we just take its equivalence class, and that is our section of the projective bundle. Okay. But the question is, does it exist? Yeah, there is absolutely no guarantee that this should exist, because we're looking for a vector field which is never zero, and who knows if this exists. For instance, if M is the sphere of dimension 2, so S2, this doesn't exist. Okay. So while for vector bundles, so fibrations where the fiber space is always a vector space, we can always make a vector field. For instance, take the vector field identically zero, and that always exists. When we have something different, when we don't have such a nice distinguished point like the zero, this is not for free anymore. Okay. And of course, if we look also at the frame bundle, an example, the frame bundle is even worse, because now it's not enough to look just for one non-zero vector field, but you have to look for a collection of non-zero vector fields which are linearly independent. So a section is a collection of non-zero vector fields which are pointwise linearly independent. Yeah, so this is, you can imagine this is something very hard. We should never expect that this is true, that there exists, such thing. In fact, we will prove this later on, proposition, that if a section does exist, then this tangent bundle is isomorphic, and okay, we'll have to discuss what isomorphic means to R to the dimension. Yeah, so it's a very specific case. This only exists in this trivial case. And of course, it's an if and only if, because here it's easy to find such a thing. But we will prove this later. Again, yeah?
Yeah, just one question. The problem with having a vector field that is never zero is when it's continuous, right? So did we?
Of course. If we don't care about continuity, we can do whatever
Okay.
we want. Yeah. Sorry.
Did we demand that the section would be continuous, or?
I did not. Sorry. Yeah, but normally we fix a category, so it's so this could be continuous, smooth,
Okay.
holomorphic. Yeah, whatever we're gonna care about. Yes, of course. I mean, here functions. If we just talk about functions, I'm not asking any continuity. I need to fix some kind of degree of regularity. So here's when I wrote CK.
Okay, thanks.
Of course. Yeah, of course, this was an imprecision on my side. I should have specified that this has some regularity. Otherwise, of course, it's very easy. Same here. Yeah, so collection of non-zero. So when I say vector fields, when I write vector fields, usually mean continuous, at least continuous, if not directly smooth. Yeah. So we will talk about continuous sections, holomorphic sections, smooth sections, etc., etc. Okay. So why should we care about any of this? Why? should we care? Well, usually natural fibrations. So when I say natural, I mean things like the tangent and all things related to the tangent. So for instance, this or this, or even, I don't know if you know about this, I think you do, but like the cotangent bundle. Have you ever heard of this? Cotangent one? Yeah, this one, and of course then, yeah, the related ones, etc., etc. So basically everything that can come out of the tangent bundle, because the tangent one is like the most natural one, but anything that can come out of it provides information about the topology, quite surprisingly, of them. And I think the peak of this understanding of how fibrations relate, so the peak of this understanding in our course, of course, is going to be the RAM cohomology. To be cohomology, actually not only the RAM cohomology, but cohomology in general. So you definitely heard of the RAM cohomology, both of you? Yeah, okay. So yeah, I assume I mean, you've heard of this, the RAM cohomology, which is the one of differential forms. And actually we will say a couple of words about that. But there are different kinds of cohomology. So if you remember, tiny spoiler, if you remember in the RAM cohomology, you have to consider something like a kernel over image, right? And there is a more general way to do this. So, and yeah, the way we will do is the so-called check cohomology. So we will see the RAM cohomology as a special case of check cohomology. And this check cohomology is some very abstract way of thinking of cohomologies, which is very powerful. And in fact, we will study these check cohomologies in general, not just how they relate to the RAM. Okay. And maybe the last thing I want to say for this introduction is to study all of this. We will also need maps between fibrations. And let's just do a quick example. So we knew that functions, let's say smooth functions, correspond to sections of m times r into m. Yeah. And now you know that you can take the differential of f of one form and one forms. So not just this differential one, but just one forms in general are sections of the cotangent bundle. Did you know this? That one forms somehow relate to this thing. You might have seen it, maybe you forget. Doesn't matter. We will definitely do this in very much great detail in a bit. This is just an introduction. So one forms somehow relate to section of this. And so we already see there is a map between sections of this trivial thing and sections of this cotangent bundle. And you know that this goes further, right? Because then you have two forms. And there is the so-called bundle of two forms, which, okay, whatever it is, it has, of course, it's related to this, but we will define it properly. And then you can keep going. And this is what gives you the RAM complex and blah, blah, blah. So this is kind of the end point. I mean, this is the end point of what you know, and now I can explain you things now. But the beautiful thing is that we will see all of this kind of putting arrows between fibrations. Yeah, this is, just think of this as a way of putting arrows between fibrations and between sections of fibrations. That's very important. And we will see that this comes down to some much more general theory, which is this check cohomology things. Okay. Since we will talk, as I was saying, not only about fibrations, but about sections of fibrations, a very important thing there is the notion of sheaf. So to study this, we will define sheaves, which are basically collections of, which are basically collections of sections. They're actually much more complicated of that, but we will see that, I think, in maybe 2 months from now. So no need to get into details right here, right now. Perfect. Okay, so now it's time to start with the actual content of the course. So today and tomorrow we will mostly review things that I hope you already know. And then from next week we will actually start with something completely new. So we started with a definition. Take M topological space. And we say that M is paracompact. This is what we're defining, paracompact. If for every open covering uj of M, so with this I mean, you know what an open covering is, there exists a locally finite refinement. What this means, what is a locally finite refinement? That is a covering Vi of M such that for every I there exists a J such that Vi is contained in Uj and W and for every P in M there exists W open neighborhood. So neighborhood I will always shorten with NGH. Yeah. Open neighborhood of P such that W intersected Vi is empty, but for a finite number. Finite number of i's. Okay, so this is the definition of paracompact, and the reason we need it is to define manifold. Yeah. So I know that you know what a manifold is, but I still think it's all made a mess. Sorry. I'm coming. Sorry, I touched the wrong thing. Okay, this will work. Okay, so now let's define what a manifold is. So paracompact, Hausdorff. So you know Hausdorff means T2. Hausdorff topological space M is a differentiable manifold, of class CK, and here K can range between technically zero, but when it's zero, you don't talk about differentiable manifold, you talk about topological manifold. So we're gonna stick with from 1 to infinity, so infinity included. And in that case, we speak about smooth manifolds or even omega. And this is when we talk about analytic manifolds, okay? This is smooth analytic. If it admits an open covering uj with j in some set of indices with homeomorphisms phi j from uj to its image, and you want to say that this image is contained into some Rn, and these are open sets for all j in j. And furthermore, we ask that such that if ui intersect the uj is non-empty for I and j, then this map phi j composed phi I inverse, which goes from phi I of the intersection into phi j of the intersection, is ck. Yeah, so the same k that we have here. Okay, and then we'll just do a quick drawing, which again you've probably seen many times. This is our, so here we're in M, yeah, this is the level of M, this is our UI, this is our UJ, this is our intersection, and here you have your phi I, and this is now just an open subset of our N, and here you have your phi J, and here you have your other open subset of our N. Okay. And what you're, so now this is in our N, and this is in our N, and we said the manifold is CK if this composition, so if you go this way, or equivalent to the other way, is a CK map, okay? And since, of course, the inverse of phi j composed phi I inverse is phi I composed phi j inverse, we're not only saying that this is CK, but also the inverse is CK. So in particular, this case infinity, this is a diffeomorphism, okay? And the set of pairs, I'm sorry, I have a very bad looking curly bracket, but this is my curly bracket, is called an atlas. And one specific pair, one pair uj phi j is a local chart. Okay. Similarly, a complex manifold, sometimes called also holomorphic manifold, is the same, but with Cn instead of Rn, and holomorphic instead of CK. So what I mean here is that here, instead of having Rn, we will have Cn. Yeah. And this composition is holomorphic. So this is what we define to be a complex manifold. And of course, this is not just holomorphic, but it's a biholomorphism, meaning a holomorphic map, which is bijective. And this actually implies that the inverse is holomorphic as well. So it's not like the real case when you need to ask that the inverse is smooth. This is automatic, it's for free. Okay. Now, one more definition. Given two atlases, uj, phi j, and vj, psi j, for a manifold M, we say they are compatible. This is what we're defining. If for all j and k such that uj intersected vk is non-empty, the map phi j composed phi k inverse in the correct domain, so phi k of uj intersected vk into psi j psi of uj intersected vk, yeah, is ck. Okay, so k is now is bad, is of the correct regularity. Yeah, okay, I hope you know what I mean by this. Now I made the mistake of using k here. But if the two atlases are CL, yeah, they're CL for some L, then you want this map to be CL. Okay. And an atlas is maximal if it contains all atlases which are compatible with it. Atlases which are compatible with it. So one thing you should notice here is that if two atlases are compatible, the union of these two atlases is again an atlas, right? So the idea is that by taking just the union of everything like this, you will get to some maximal element, and this exists by Zorn lemma. This exists by Zorn's lemma. And for this reason, we will always assume that our atlases are maximal. Like we don't lose anything from it. And which basically means that, you know, if you have a property which is okay, you let's say, oh, let's take a local chart. Then we say, oh, we can restrict the local chart because maybe we need to prove something local. Then this is still a local chart, okay? Because we can always restrict this thing, and it's always in the atlas because the atlas is maximal. This is the practicality of that. Okay, so now let's define also what is a smooth map between two smooth manifolds. So Mn smooth or complex manifolds. A map F from M to N is smooth or holomorphic in the case of complex manifolds. So this is what we're defining. If for every point in M, there exist local charts U phi of M and V psi of n such that P is in U, f of P is in V, and the map psi composed F composed C inverse from phi of U to C of U to C of B, sorry, is smooth or holomorphic, of course. Okay, so again, the problem here is that if you have M and N and you have map here F, you're not really like, we know what a smooth map is only for maps from Rn to Rn or holomorphic from Cn to Cn, or well, Cn to Cm. So of course the dimensions can be different. So you're not allowed to just check this, you have to check this locally. So you just apply phi inverse and you apply phi, and now this is in our N, this is in our M, and we know what it means for these maps to be smooth or holomorphic. Okay. And of course, one thing that one should check. So the first exercise is that this definition is independent of the choice of local chart. And I'm confident that you can prove this in one line or even in your head. Okay, so let's start with our first examples. And I want to actually show you some pathological examples because I'm pretty sure you've seen like a lot of manifolds by now. But yeah, I want to show some, let's say, weird examples which maybe you have not seen, hopefully. And if you have seen them, it's a good reminder that one should be careful. So we take the set of real numbers, but remember that I also need to give you an atlas. So this R comes without a manifold structure. Yeah, so I need to give you an atlas. And let's say that this atlas is the standard one, meaning that we have only one chart and phi of x is just x. Okay, so this is the most standard structure you can put on R. It actually gives the standard structure of R. And on the other side, we have another manifold, R again, but we give it a different atlas. So again, only one chart. But now this chart is x cubed. Okay. So these maps are homeomorphisms. That's the only thing we ask to these maps, right? This is an homomorphism because it's identity. This is an homeomorphism because it's continuous. The inverse is cube root of x. It's also continuous, so this is a homeomorphism. But M and N are distinct manifolds. So these are two different manifolds because the atlases are not compatible. Atlases are not compatible. And to see this, we just observe that phi composed phi inverse of x is cube root, and this is not smooth. They're the same as topological manifolds, but they're not the same as smooth manifolds. Okay. Nevertheless, they are diffeomorphic. So consider their f from m to n, which sends x to the 1/3. And the question is it smooth? And of course, if you just think of m of n as R, this is not a smooth map, right? But we have to apply our definition. So we have one local chart. We apply the inverse, we have M, we have F, we have N, we have another local chart, and we just have to see what happens. Okay, phi inverse, just take X to X, because this is the identity, and this sends us to X to the 1/3, M psi, X third. So this is X. So this is smooth. Okay, it's smooth, and of course the inverse sends X to X to the third is also smooth. So the two manifolds are diffeomorphic. And diffeomorphic, of course, means that there exists a map F from M to N and an inverse, also smooth. Blah, blah, blah. Okay, let's give another example now with complex manifolds. Oh no. Okay, so now our topological space is D, the unit disk. Yeah, so the set of complex numbers of norm less than 1. And our first atlas, sorry, then first atlas, so it's a complex manifold with atlas D. So again, only one chart, D and phi. And again, phi is just identity. And then we take N, again, D, but with a different atlas. D psi, where psi from D to C is any homeomorphism. Yeah, and you know that, of course, D and C as topological spaces, they are definitely homomorphic to each other, because one is disk and the other one is R2. So we know that they're homomorphic to each other, so this psi exists. And of course, this psi doesn't care at all about the complex structures that we have here. Yeah? And the fact that M and N are not bilomorphic to each other. So to prove it, by contradiction, assume that there exists a G from N to M bilomorphic. Yeah, so we assume that this exists. So what this means is that phi composed G composed psi inverse from C to D is a holomorphic map. Yeah. But then by Liouville theorem, this means that it's constant. So this means that G is constant, which is of course an absurd. Okay, so the point is that we have these two manifolds, which are really different manifolds from a complex point of view. Yeah, they're really not the same. And on one of them, we put this standard chart, which is just identity. And on the other one, we put this very topological chart, which kind of forgets that this is a disk, like a complex disk. Yeah, it just treats it as R2. And the point that these are not bilomorphic, because then if you have a map from the second disk to the first, then if you look at in the charts, this is actually a map, a holomorphic map from C to D. Yeah, this is what we see here. And holomorphic maps which are bounded are constant. This you know. Both. Yeah. Okay. So of course, if this is constant, then G is constant, so it's not a bilomorphism.
Just one question.
Yeah.
How do you call it? We have the three maps in a row. Why do they originate in C?
Yeah, because if you go back to the definition of a
Of
smooth map,
psi.
so you have a map between smooth map between a map between smooth, or let's say complex manifolds,
Hmm.
is holomorphic if the map from U. Sorry, no, this should not be U. This should have been phi of U, and this should have been phi of V, C of V. If the map from below, so from the image of the chart, you go back to M, you apply your map, then you go onto the chart. So if you look at it here, what you have is, okay, we have M here, N here. So forget that this is really the disk. And this is our, sorry, the opposite, N to M, N to M, N to M. This is N to M, G. And here we have our psi, which goes to C, correct? And here we have our phi, which goes to D.
Psi. It's surjective to C.
Yeah, it's
Yeah. Okay. Now I get the contradiction.
Yeah.
Thank you.
Of course. So time, okay. There are other examples which again you should be familiar with. So I will give them as an exercise in case you're not familiar with them. Give a smooth structure to GLNR and a complex structure to GLN. See? Very easy. So again, this should be something you do in your mind. If it's not, think about it. And then I think this is going to be our last example for today. And that is the projective space. And okay, we define an equivalence lens on Cn plus 1. And we're going to do complex projective space, because actually it's going to be very important for us later, by saying that P is equal to Q if and only if there exists a non-zero complex number. So this star here means non-zero complex number. This comes from algebra. Yeah, when you have a group, or yeah, sorry, when you have a ring, you take the set of the multiplicative group of the ring. So that's what the star is coming from, such that P is lambda Q. And we define the complex projective space of dimension n to be just equivalence classes of this. Okay. And we also have pi from Cn plus 1 minus 0 to Cpn. The projection, yeah, the quotient. Projection. And one thing that we can observe, so let's say observation, pi, if you restrict it to the unit sphere inside Cn plus 1, so you know Cn plus 1, you can think of it as just R to n plus 2. So the unit sphere in there is S2n plus 1. This is surjective and continuous. Yeah, think about it. For every point here, there exists a unique no, not unique, but there exists a representative on the sphere. So this is definitely surjective. And continuity, it's yeah, I think it's obvious. So this gives us that CPN is compact, because it's the continuous image of a compact set, and also connected as being the continuous image of a connected set. Okay, so this is a couple of things about projective space. Exercise. Prove that CPN is Hausdorff. So what I'm trying to do here in this example is to prove that this projective space is in fact a manifold. Yeah. And so we need to show that it's paracompact and Hausdorff, first of all. So Hausdorff is the exercise, paracompact is for free because we know it's compact. So in particular, it's paracompact. And now what we want to do is define charts. Because this is what gives us this thing. Did you ever see the projective space as a manifold? So do you know the charts, the standard charts here? No? Okay, perfect. Yeah.
I forgot a bit, but is it something like say n is 3 x divided by y, and then everything divided by one of the coordinates?
Yeah, yeah, okay, but since maybe it's not so something you remember so well, we'll just do it again. So homogeneous, because this will be actually, I mean, we will do quite some very important examples on the projective space. So these are so-called homogeneous coordinates. And this is just the equivalence class. Equivalence class of z0, comma, zn in cn plus 1 minus 0. Yeah, so the cn plus 1, I don't add that zn plus 1, I just add that z0 at the start. Okay. And now we define uj, and this is going to be an open set in CPN. So all these equivalence classes such that zj is non-zero. Okay. So this is a subset of CPN, and it's open. And of course, we also have that if you take the union over j, union over j, yeah, this is j from 0 to n of uj's. Sorry about this. This is the whole of CPN. Yeah. So in particular, this is an open covering, which makes it a good candidate to be charts, of course. And so we define phi j from uj into actually the whole cn. This is surjective. That takes z0, cn, and sends it, as you were saying, to the n tuple, z0 divided zj, and zj you see on uj, zj not 0, so this is perfectly allowed. And then you continue, so you have z1 over zj, but then when you get to zj, you omit it, you skip it. So this symbol here means skip it, okay? And then here you have your zj plus 1 over zj, and then you continue all the way to cn over zj. So these are only n of them, because you have n plus 1, but then you skip this term here. And we observe that this is a homeomorphism. And how do we see that this is homeomorphism? Well, we just see the inverse. Because now we take some z0, and again, we like to skip the zj, and then we go all the way to zn. So of course this is cn, but like we name the coordinates in this weird way. We go from 0 to j minus 1, and then from j plus 1 to zn. and we just send this to Z0, Z1. And now at the jth position, we just put 1. And then we go all the way to the end. Okay, and you see that this is an inverse. And they're all very nice and continuous. So this is a homomorphism. And now, so to see that this is actually a complex manifold, and to conclude today's lecture, we need to see that the transfer of charts is a bilomorphic map. Okay, so we need to check that phi k composed phi j inverse are bilomorphisms. Okay. And actually, since we're talking about holomorphic maps, it's enough to show that it's bijective, and that's for free by the way we choose the domains, yeah? And just holomorphic, because if you have a bijective holomorphic map, is for free a bilomorphism. Remember, this is not true for smooth maps. So for simplicity, let's just say that k was 1 and j was 0. Okay, so we just work with the first two coordinates and it's easier to write everything. But otherwise, of course, this works in general. So we start from Cn minus, oh no, Z1 equals 0. And why is this? Because this is nothing but phi 0 of U0 intersected U1. Yeah. So U0 intersected U1 is the open set in CPN where Z0 and Z1 are not 0. And so the Z0 equals 0 just disappears here because it's the correct local chart. And we remain though with Z1 different than 0. Then we go into this intersection. Okay, and this map, we know it. We go to 1. So this is phi 0 inverse. 1, Z1, blah, 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 Zn. Okay. And here you have our phi 1 or phi k in general. And here we go in phi 1 of U0 intersected U1, which is, you can think about it as Cn minus, here I want to use a different name, like I want to call it W1 equals 0. And I think you understand why I want to use a different name, because this W1 is the first coordinate here, but it actually corresponds to Z0 in the projective space. Okay, so I hope you understand why I want to use here coordinates W1, Wn instead of just Z1, Zn. So when we go, okay, we have to divide everything by Z1. Oh, sorry, this shouldn't be, yeah, like this. So we get 1 over Z1. Then the second coordinate is skipped. So we just go directly to Z2 over Z1. Blah, blah, blah. Zn. And we see, okay, we know already it's bijective because these were homomorphisms and the domains are fixed so that this stays bijective. And is it holomorphic? Well, it is because these are simply rational functions and Z1 is different than 0. Okay. So we're good. These are bilomorphism, and this proves, in fact, that CPN with this specific structure, with this specific atlas, is in fact a complex manifold. We should stop at 45, correct? Okay, so I think we do have time for, oof, okay, this is a bit long. No, okay, let's at least start it, because anyway, we meet tomorrow. So I hope this, you will not forget all of this. So the last example here is the Grassmannian. Grassmannian, I hope I'm spelling it right. Grassmannian. Have you ever heard of this manifold? Yeah, the Grassmannian. Okay, perfect. So this is a generalization of projective space. Of projective space. and we define GKN of C to be the set of all vector spaces, vector space of dimension K. And we want to show, we now show that GKNC is a complex manifold of dimension K times N minus K. And the way to see this is to consider JKN C as a quotient. Actually, wait, too fast. Okay, so let MKN C to be the set of K times N matrices with independent rows. Okay, so basically what we're saying here is that rows of these matrices generate spaces here. Okay, so let's consider this map, which goes from KNC to GKNC, which take a matrix A, and it sends it to the span of the rows of A. Okay, you have K rows of length N, so this is something in Cn, and they're independent, so they span a space of dimension K, so an element of the Grassmannian. Okay, and an observation should be that okay, when do two such matrices produce the same object? So when is this happening? When is pi of A equals pi of B? And when basically is when the row of K's can be expressed as a linear combination of the rows of B. And this is equivalent to say that there exists a matrix G in GLK, not GLN, but GLK, such that GA is equal to B. Okay, so this is saying that you're rearranging the rows of A. Okay. So we can think, of this Grassmannian as the quotient. Okay, so this is just the quotient as a vector space, and you can think that you have a group acting on this topological space, so we can take the quotient. Okay. Note that this is very similar. I mean, this is exactly the same thing you do to define the projective space when K is equal 1. So, local charts. We will actually do only one of them. So we take matrix here and let A1 AL be B. It's K times K minors. So, you know, a minor is something made out of the columns of this. I mean, since this is K times K, you just take K times K square matrix made of the rows of A, and you know that there exists a J between Y and L such that the determinant of AJ is non-zero. Yeah, because these matrices were at linearly independent rows, so one of these minors has to be non-zero. Okay. So define UJ, the set of all matrices in the Grassmannian, so not matrices, but projection of matrices, such that the determinant of AJ is non-zero. Again, you should try to draw the parallel here with the projective space. Okay. So by what we said here, Uj is an open cover. Of the Grassmannian manifold. And now we need to define charts. And we will only do it so define charts Vj from Uj, and this also will be surjective. So this is going to Ck times n minus k. But we will only do it, for j equal 1, which means the first minor. The minor made of the first k columns with the first k columns is non-singular. Non-singular means determinant different than 0. Okay, so we'll only do it for the first one, just because otherwise it's very hard to keep track of everything. So we have this matrix, and we can decompose it at this A1. So this is the k times k part, which is determinant different than 0, and B. So I'm gonna call B. No, just B. It's fine. Okay, so this is k times k, invertible, and this is k times n minus k. Okay, so you should already imagine that the important information is encoded here simply because it's the right dimension at least. And in fact, the map takes Vj of A and it sends it to A1 inverse times B. Okay, so you see this is k times n times k matrix. And we should show that this does not depend on the, sorry, this of course should not be A, but it should be pi of A. We should show that this is independent of the choice of representative, right? But that's an exercise. Prove that phi 0, sorry, phi 1, 1, phi 1 is well defined. Again, you should see the idea, I think, already in your head. Maybe to actually give the proof, maybe you want to look at it a bit more and perhaps write one line. And yeah, how do we verify that this kind of makes things work? Well, let's just look at the inverse. For instance, the inverse of phi 1. So we think of this Ck times n minus k as matrices of k times n minus k, and well, we'll just send it to pi of the identity. So this is the k times k identity matrix. Yeah. Okay. And so this was the easy exercise, and now I'm also going to give you the hard exercise. So the star means it's a bit harder. Verify that this is in fact the inverse. And that they, and they I mean not just phi 1, but all of them, they define manifold. Not any manifold, but a complex manifold. Yeah? So what you have to do, okay, you should define also the other phi j's, but I hope it's clear how to define them. So instead of taking this minor, you take the minor, the corresponding minor. And instead of having the first k rows here, first k columns giving the identity, you have the columns corresponding to the minor. And you have to verify that the composition is in fact a belomorphic map. Okay, and holomorphic in the entries of this thing. So maybe a small suggestion should just be that you don't need to compute the entries of this matrix, yeah, of this phi I compose phi j inverse of A matrix. You just have to show that they are holomorphic. And the way to do that is to remember that like the inverse of a matrix is it's always an algebraic function of its entries. Okay, and algebraic functions are holomorphic. Okay, so I think that is it for today.